Okay, cool. So we're recording now. So cliff notes for the people who joined us because I forgot to record. Last day of the Qual Prep Seminar is September 11th, which is in 3 weeks from now, which means that you've got 4 weeks until that week 0. And week 0 is normally when the quals are. They haven't announced the quals, but we've got about a month, so use your time wisely. And also we are meeting on Thursday. If you saw the mistake on the website, it's been fixed. All right, so how was Mock Qual 2?
Not bad.
Better than Mock Qual 1.
Oh, interesting. My perception of Mock Qual 2 was that it was harder to Mock Qual 1 by a fair bit.
I mean, I thought they weren't, but I thought neither of them were bad, but I did end up taking up much less room in my notebook for Mock Qual 2 than Mock Qual 1, so I guess it's easier.
Okay, interesting.
Yeah, I mean, to be fair, I thought the questions took longer to write out and compute, but I thought that the conceptual difficulty was about the same as the first one, but that might just be me having been not as prepared for the first one.
Good. Maybe this is a sign that you all are growing as topologists, and you're all going to get topology advisors, and we're going to have a big topology group at UC Riverside by next year. Should be great. Okay, cool. So I think that the plan today was to present on some of these problems. 5 of the 9 problems have people who've signed up to present, but I also have solutions for 2 and 4 written in addition to question 5. But question 5, oof, that took me a while to figure out how to do. I worked on it for a little bit, and then went and watched something on YouTube, and then worked on it for a little bit, and then ate dinner, and then called one of the other math topology grad students on Zoom, and we talked about it for a little bit, and then I worked on it by myself, and then I messaged him again, right? And I was like, wait, everything that we did was wrong, and I think I finally have the right answer, but it was it was a journey, right? So I'll talk about question 5 unless somebody else is just like, no, Jacob, you're being silly, it's straightforward, and you just do this. So I'm thinking that since we have the sign-up sheet, we'll just talk about the ones that people signed up for first. And then if we have time, maybe we'll try to go back and talk about the ones that people didn't sign up for, or more than likely, we'll probably talk about these 5 problems today. And then Thursday, maybe people can sign up for some of the problems that we didn't get to talk about yet. And then we'll talk about the remaining problems. And with this list, feel free to add your own problems. That's why I made the list a lot bigger than just the problems on the side. So if you're like, I would really like if someone could explain question 9 from Mock Qual 1, I've seen people talk about the Discord, or if there's a problem exercises to know, or hey, can someone go over this midterm or final exam problem from 2020 or something? Feel free to add that problem on the list, and then somebody else might see it and be like, oh, I can do that problem and talk about it, and they can sign up. And that this could be a good way for you all to talk about the kinds of problems that you all want to see. So cool. Unless there are any questions, comments, or concerns for me, let's go ahead and get started with question 1. Mock Qual 2.
I signed up for that.
Yeah, great.
Okay, so I'll share my screen, and I've typed out my solution. I'll show that and explain it. Okay, so this is the question. The first part is that we've got to prove that S1 cross S1 is not a retract of D2 cross D2, where S1 is the unit circle and D2 is the unit disk. Okay. So yeah, just to recall what being a retract means, as we know, if a subset of X is a retract, then A is a subspace of X, and we've got a map R from X to A such that RA equals A for all A and A. And we have this inclusion from A to X such that R of Y is identity on A. We have such a map R. So then I and R induce group homomorphisms from pi1a to pi1x at A naught, I star and R star, and they satisfy this as well, that R star of I star is identity. So that means that I star must be 1, 1 for this to be true. So we'll show that that's not the case in this particular case. So for X equals D2 cross D2, we have that pi1 of X at X0 is trivial because D2 is contractible since it's the unit disk. And we get a contraction using the straight line homotopy. But A, which is S1 cross S1, has pi1 equal to Z cross Z because pi1 of S1 is Z. So pi1 of S1 cross S1 is pi1 S1 cross pi1 S1, which is then Z cross Z. So this is Z cross Z, and that's 0. So definitely we don't have any injection from pi1a to pi1x. So I star can't be 1, 1, and so there's no retraction from A to X. So for the second part, we've got to show that if X and Y are Hausdorff spaces and Y is going to be connected, then suppose P from X to Y is a covering map and the fiber P inverse Y0 consists of 2 points for some particular Y and Y, Y0 and Y, then we've got to prove that for every Y and Y, the fiber P inverse Y has exactly 2 points. Okay, so given this map P, and since it's a covering map, that means that for the given Y0, P inverse Y0, okay, that's given to be exactly 2 points. So P being a covering map means that there is a neighborhood of Y0 which is evenly covered. So yeah, so we're actually going to take the set of all points which have an inverse image of 2 points, exactly like Y0, and basically we're going to say that this set Y2 is the whole of Y, and we'll show that by saying that Y2 is clopen. Since Y is connected, that would mean that Y2 is the whole of Y. Okay, so as we were saying, this is what we're going to show, but now for Y0, which is given, there's a neighborhood which is evenly covered since P is a covering map, and so that neighborhood, say UY0 is a disjoint union of neighborhoods of of open sets in X, open subspace of X, open subsets of X, such that P inverse of UY0 is the disjoint union of those open sets B, and P restricted to every VI is a homeomorphism from VI to UY naught. So basically we've got that every point in UY naught, the neighborhood of Y naught, has exactly 2 points in its fiber. So that means that this set Y2 it's open because we've gotten a neighborhood for every such Y0. So we could have, so Y0 is a particular point, but we could have done this for any Y in Y such that P inverse Y has 2 points. So since we can find a neighborhood for any such Y in Y2, that means that Y2 is open. So now we're going to show that Y2 complement is open as well, so that then Y2 is closed and then Y2 is clopen. Okay, so suppose we take an arbitrary Y and Y2. Oh, I'm sorry, that's what we just did. So this is what we got, that by this, since we've got a neighborhood of Y for every Y in Y2 in Y2, so Y2 is open. Okay, so this is what the covering looks like for points Y and Y2, which means that they have exactly 2 pre-images. Okay. Yeah, that's what we proved. Okay, so now for Y2 complement, if we take a random point Y in Y2 complement, then that means that P inverse Y has some R points which are not equal to 2. So then we can get an evenly covered neighborhood of Y, since again P is a covering map. So we can get a neighborhood of Y such that, okay, so UY, a neighborhood UY such that P inverse of UY is the disjoint union of open sets again, and all points in this neighborhood UY have exactly R points, like we did for P inverse of X equals, which had 2 points in the case of Y2. So similarly, we've got a neighborhood of Y in Y2 complement as well, which has the same number of points, whose inverse image under P inverse, inverse image under P has the same number of points as P inverse Y. So that means that Y2 complement is open. So then we got that Y2 is both open and closed, so it's open, but since Y is given to be connected, so then Y2 has to be, Y2 is also non-empty, so it has to be equal to Y. So that means that all points of Y have exactly 2 inverse images, 2 points in their fiber, given that when we're given that a single point has 2 images in its 2 points in its fiber. So we proved the second part as well. Thanks. Any questions?
I have a question, not on the proof, because the proof was excellent, I thought, but just like I understand that D2 cross D2 is simply connected because, right, it's path connected and semi-locally simply connected, so it's equal to pi1 of D2 cross pi1 of D2, which is 0 cross 0.
Yeah.
At the same time, though, it seems like D2 cross D2 deformation retracts onto S1 cross some element, right?
Why?
Just in my mind, it seems that way. Just take the solid torus and crunch it down until it becomes a circle.
But like,
Yeah, the solid torus is D2 cross S1. Right, you take the disk and you rotate the disk around the y-axis, right? Like you take a disk somewhere over to the right of the y-axis and you rotate that around.
Oh, okay.
also
Yeah,
like if that worked, wouldn't it? What isn't what you're picturing saying that D2 deformation retracts onto S1?
Yeah, ignore the second coordinate and then you just get a deformation retract in the first coordinate. D2.
Which is like
Yeah.
the first thing we do to prove that this is actually worthwhile mathematics.
Yeah. Okay, thank you for that.
So the only thing that I'd say here is that your definition of a retract is slightly not correct. It didn't affect the rest of your proof, but in your definition of a retract, you said that you have to compose with the inclusion map.
Yeah.
But you don't have to compose with the inclusion map. I can be any map which makes R composed I equal to the identity on A.
Okay.
You can see that the definition is actually given in the last Mock Qual. If you read question 4 of Mock Qual 1, you get that as long as that composition is the identity on A, then capital R is retract. So I can be fuzzier.
Okay.
Yeah.
Thanks for letting me know. Okay then.
But yeah, otherwise it was exactly what I had in mind for the solution. So good job. Since you did tech it up, there's a link on the website to an overleaf page with the LaTeX file. So if you could include that in the LaTeX file, so that way other people can see your solution, that would be great. Feel free to credit yourself.
Oh, you've been adding the code which made up this file into a bigger file?
Yeah, so on the website underneath the PDF link, there's an overleaf link with solutions that you all can edit. So
okay.
Yeah, so since you already have it teched up in Beamer, if you could just copy, paste, and then remove the begin frames and end frames, then that would be great.
Oh, sure, yeah.
Okay, then it looks like question 3 is the next question that someone signed up for. I think that's Shanna and Catherine.
Okay, I will share my screen. Okay. All right. Shannon's gonna make sure I don't say anything too silly.
Too brilliant. Yeah.
All right. So this is the question. So XY denotes the set of homotopy classes of maps from X to Y, and there are 3 parts. The first part says that prove that every contractible space is path connected, and space is contractible if the identity map on the space is null homotopic. So in other words, homotopic to a constant map. So for part A, suppose that X is contractible using that definition, and therefore we have this continuous map here. And so basically, what I'm going to do is I'm going to use that homotopy to connect X1 to the constant, connect X2 to the constant, and then use transitivity of path connectedness. So that's what this picture is here on the right. So let's see, let X1 and X1, X2 be an X, and then define this F1 of T to be that homotopy, but I'm going to fix the X x1 in that first coordinate. This is continuous because f is, and then just to check, so f1 of 0 does give me x1, f1 of 1 does give me the constant. So this thing in blue is that first path. All right, let's see. And then similarly, I'm going to define f2. So f2 basically does the same thing, except I'm going to fix the first coordinate x2 in f. And then this is the pink path that goes from x2 to k. And then just by transitivity of path connectedness, I know that x1 then is path connected to x2. Those are arbitrary, so the whole space is path connected. Yeah. Shannon, did you want to add anything?
I think you're doing great.
Okay. All right. So for part B, we want to prove that if y is contractible, then the size of xy is equal to 1. So you can think of this as all of the maps from x to y are homotopic to each other, or they're all homotopic to a single map. So basically what I'm going to do is I'm going to show that they're all homotopic to a constant map. So again, since y is contractible, we know that the identity on y is homotopic to this constant map, which I'm going to call h of y is equal to c. So c is just some constant in y. And then let this capital F now be that homotopy between the identity on y and the constant function h. And then we know that f of y0 is equal to the identity of y, which is y. And then f of y1 is equal to h of y, which is c. Okay, so now I'm going to let f just be any continuous map from x to y. So in that group of maps, and then let g be a constant map that goes from x to y. And I guess the like key here is that I define it to be the constant map that goes directly to that point C. So this was kind of my idea here, was that basically we map over F, and then capital F is going to take that mapping to C. So to formalize that, let g of xt go from x cross 0, 1 to y, and I'm going to define it by plugging f of x into f. And so this is continuous because both capital F and F are continuous. And just to check, so g of x0 does in fact give us f of x, g of x1 does in fact give us c. So now I have that f is homotopic to that constant function. And then since f was arbitrary, that means that all of my functions, my continuous functions from x to y, are homotopic to that constant function. So they're all homotopic to each other. And thus the space would just have that class, the set of equivalence classes of those functions would just have one element. Yeah. I miss anything? Okay. So last part is if x is contractible and y is path connected, then we also get that there's only one equivalence class in that set. So same thing, using the definition of x being contractible here. So now I have the identity on x, and it's homotopic to a constant function h, which goes from x to x. And so let f of xt now be this homotopy equivalence between those two maps, and you get the usual thing. So f of x0 equals the identity, f of x1 is equal to h, which is that constant map. So I think the difference between this part and the other one is that what's going to happen is we're going to get that all of our, like if I pick an arbitrary f this time, it is homotopic to a constant map, but each f that I pick is homotopic to a different constant map. And so they're all homotopic to different constant maps, but then because of path connectedness, I can show that any two constant maps are homotopic to each other. So that's where this is going. So this was sort of my idea here that hopefully I've explained accurately. So what I'm going to show is that, well, I guess what this is showing here is that the function f of x is homotopic to the constant function f of c. So I'm kind of going the other way. So that's this homotopy here. Again, everything is continuous because capital F and F are. Okay, and then I guess I said this already, but just to reiterate, so every continuous function f is homotopic to a constant function, but they're all homotopics as different constant functions. So to rectify that, my claim is that if y is path connected, then all of the constant maps are homotopic to each other. So say that g1 and g2 are just two constant functions from x to y. But then I know that y is path connected, so I can connect my two constants via this continuous path. And so I can just define the homotopy to be that path in between them. All right, so therefore all of those continuous functions f from the beginning are homotopic to a single constant map. And so the number of equivalence classes is again just 1. And yeah.
Were we right about that, Jacob? That one was a little tricky, but the trick was to get, everything lined up to the same constant. Or how would you approach that? Like
Exactly like this.
Okay.
Yep. Yeah, this is a very clean solution because it's like I use this condition to get me to here, and then I use this condition to get me to here, and then I use this condition to get me to here, right? Like it's very much like I was given 3 puzzle pieces and I'm gonna use all 3 of them, right? Which is very nice. But yeah, you are exactly right. Some people find this part C tricky because they don't realize why they need path connectedness in the second component, right? Because they just go, but they're both the constant map, and they just, right? That subtlety, which you very well explained, is that different functions are homotopic to different constant maps, right? And you need to be able to connect those constant maps, and that's exactly how you do that.
Yeah, Jacob, I had a question kind of philosophically. So on, it's interesting that on part B, you only needed y to be contractible, right? And then you got the homotopy class to just have one element. And there was no restriction on x, right? And then to get, and then if you have x being contractible, then you need y to be path connected.
Yeah.
So it's kind of
Yes, my way of like philosophically understanding that is these are essentially like in the category sense, right? Like initial and terminal objects, right? Like there's up to homotopy only one map to a contractible space, because a contractible space is essentially a point. But to if for the terminal object, the contractible x, there are arbitrarily many maps out of it as that just pick out elements of your codomain. So you need to actually be able to then trace them out via some sort of connecting map. Otherwise, you're counting the number of path connected components.
I like that. That's nice.
Yeah, that is literally how I think of it. The way that I think of these is, well, you either contract the end point, the starting place to one point, and then just treat it as if it's a 1-point space, or you contract the target to 1 point and treat it as a 1-point space.
Yeah.
I think that's better than what I was going to say. So yeah, that's a great point of view. Just view your contractible sets as 1-point spaces and then see what happens to them. Okay, cool. Okay, so I know that problem 5 is next on the list, but I'm gonna,
I think I was going to be doing question 2, but then like my internet failed. I don't know what happened in the interim between the first presentation and Catherine's.
on the sign-up sheet that I'm reading, you only signed up for question 8.
Oh, I signed up for 2, but
Oh,
as well, but
I mean, it, yeah,
my bad.
yeah. Okay, I mean, would you like to go back and do question 2? That's sort of fine.
Sure. I mean, it doesn't
Great.
take, sorry, I thought I signed up for 2 and 8. So, can everyone see my screen?
Yes.
Okay, so what we're given is that we have RND, the metric space with the Euclidean norm, and we want to, and we also have A in Rn is closed. And we want to show that the function distance from X attains a minimum on A for any X. And actually, this problem is really, first of all, this problem is really just a real analysis problem, which justifies my belief that point set topology can be done just by, like, you can skip point set topology if you take an analysis class. But the other is really you just have to change your perspective slightly, and then all the definitions mean that the problem is immediate. So the thing to know is for D blank X to attain a minimum on A, what we're asking is that there exists a Y so that we want to know that the infinitum, this Y in A, is actually attained for some Y in A. But note that the infinitum this statement generates a sequence Yn contained in A, where Dyn X goes to, I'm going to just call this M because I'm lazy, goes to M as N goes to infinity. But A is a closed subset, so contains all its limit points. So this actually Yn has to go to some Y in A, and we're done.
Okay, so why does Yn converge?
Because of the fact that the distance function works nicely, essentially.
So this is one of the reasons why you're given the hint that A is not assumed to be bounded, right? You're supposed to invoke the Heine-Borel theorem at some point to say that there exists a convergent subsequence which converges to a point, and then that point is in your set because your set is closed and contains its limit points. So if Yn converges, then the point that it converges to is in A, but
I don't actually think you need to. I don't think you need to do that. I think you can use the triangle inequality to show that any sequence generated this way will converge, right? Because you've got a fixed X, right? Because in other words, you could take like you can make A bounded by, okay, right? So take take X ball of radius R centered at X, close, intersect with A. Now A is closed and bounded. So, and similarly, the line of argument that the line of argument I had was, oh, well, this will actually converge because I can do a, everything is being compared to X. X is fixed. So I can actually force any sequence generated this way to converge.
Okay, so here's a counterexample to saying that any sequence converges. Take, say, the unit circle sitting in the plane. X is the origin, and your sequence yn just alternates between +1 and -1 on the x-axis. Right?
Okay.
So, this certainly satisfies your condition in that the distance goes to the infimum. In fact, the distance is the infimum for every point. But at some point, you need to invoke that there exists a subsequence that does converge, and that convergent point is in the set. However, in order to counteract your argument that all point set topology is linear algebra, if you
Not
put on
linear
your
algebra, real analysis.
real analysis. If you put on your topologist hat instead of your real analysis hat, this problem is even easier from the outline that you described.
Why? How so?
Because the distance function is continuous.
That was the line of reasoning that I was thinking of.
Yeah,
When I actually wrote this, but that's not requiring you to have a topologist hat on. That is how I would prove it in a real analysis class.
well, so
But
here's one line.
Does it help you?
So the line that I was thinking of was that you just take the image of A under this function, which is a closed subset of the closed interval from 0 to infinity. Because it's the image of a closed set under a continuous map. Or no, sorry, you intersect this with a closed ball, and you get it's the image of a compact set under a continuous map. So it's compact and then it's closed because you do the normal Hausdorff argument. And then you say, oh, closed sets in Rn attain their minimums, and then that's the argument.
Yeah, I mean, but that's basically this, right? Do this. Now you've got a bounded set.
Yeah, in either case, the reason that you were given A is not assumed to be bounded is because you're supposed to say, hey, if I take like the two ball around the closed two ball around X, that's a compact set. You intersect that with A, you get another compact set, and then you do the nice things that compact sets do, right? Including the like sequential compactness arguments and things like that. So, all right, cool. Are there any other questions or comments for our rule? All right. Anthony, would you like to talk about question 7?
Yes. 1 second.
Thanks again for the presentation.
Okay, everybody can see that? Right, so we have a smooth map from RPN to R, and we want to show that there are distinct points in RPN such that the differential at both points is 0. So the trick here, I guess, is to note the fact that RPN is compact. So we can apply the extreme value theorem. RPN is compact. Extreme value theorem. So F attains minimum and maximum. Suppose minimum of F is FP. Max is F of Q. In particular, right, if at minimum and maximum, the partials, well, strictly speaking, the partials of the coordinate representation will be 0. So the matrix of the differential will be 0, hence the differential is 0. And then the last thing to do is to verify that we actually have 2 distinct points. If they are already distinct, like if the minimum of F is not equal to maximum of F, then we're done. Otherwise, right, if the minimum and maximum are the same, then the function is constant, in which case every point has 0 differential. Have DFP equals DFQ equals 0. And that should finish it. Any questions?
Yeah, I've got a quick question. I did this same proof, but then the same concern that I've brought up with, like, you know, the n choice of n, is RP 0 a single point?
Did we assume for this problem that n was at least 1? Or maybe that wasn't part of the question. Yeah.
Right.
Yeah, I
the
think that
process-
RP0 is a single point.
Yeah, because
But-
S0 is 2 points. So if you identify those 2 points, then you should get 1 point.
Yeah. So I mean, it's literally just
Yeah.
just me like wanting to check that, because the proof technically does fail, but who's dumb enough to ask about RP0?
Nice proof. I admit that my proof does not look as good as that proof. I went through and was just like, RPN is compact, therefore it's n connected, therefore its image is a closed interval, therefore it obtains a minimum and maximum. Like I didn't, like I should just use the extreme value theorem. I went through the steps of the extreme value theorem instead of saying it. So that proof is nice. Right, any other questions, comments, or compliments for Anthony? Okay. Then Raul also signed up for question 8. So you'd like to go ahead and take it away with number 8.
Okay, so I actually really enjoy, and I'm going to sort of try and go through like all the thought process behind it, because I didn't go like it was basically like I didn't have the answer right away. It involved a lot of like discovery, and I think it was important to do that. So I guess I'll try and go through everything that I did. So we're told that we want to find smooth maps going from M to N to P, labeled F and G. These are smooth with constant rank, but this one is not constant rank, and we're also told that we can actually choose this to be going from R to R2 to R again, with this is GF. And what I did is what I did is I sort of worked backwards. I said, okay, so what does it mean for GF to not be constant rank? Well, GF, the differential of GF is just a differential of the map R to R. So it's really nice. What we need is that DGF at some point P is 0 and at some point Q is not 0. This is the only way for a map from R to R to not be constant rank. So in particular, what we're going to want is at least that the what we're going to do is we're going to say we're going to compute DGF as a function of P, and we're going to state that we want this to be linear in P. So let's see what is and we're going to just deal with Jacobians everywhere. So we have we're going to have to compute the Jacobian. And then we also note. So if we write JGF of P, this is going to be equal to JG of F of P dot JF at P, where J denotes the Jacobian matrix. So we're going to compute JG and JF in order, and then compute in the abstract what these are to make a linear in P function. And then we're going to work backwards just by using the fundamental theorem of calculus. So JG so first of all, what is G? G is a map from R2 to R. So JG is equal to del G del X1 comma del G del X2, and F is a function from R to R2. So we can write F is equal to F1 comma F2. So then JF is equal to how do I want to notate this? F1 prime, F2 prime. Sorry if you hate my mixing of Leibniz and Newton notation. I'm deciding on the fly what notation to use. So we have all the parts here now. We say that we compute, well, del G del X1 comma del G del X at F of P, and this is being evaluated at P.
Well, can you say that one more time? You froze for about like 10 seconds.
Oh, sorry. So remember, we're looking for JGF at P. So that is JG at F of P. So the Jacobian of G is this, evaluated at F of P, dotted with the Jacobian of F at P, which is this.
Thank you.
So then we just expand this. So this is equal to del G del X1 at F of P times F1 prime of P plus del G del X2 at F of P dot F2 prime at P. So now there are a very large number of solutions to this. So we just need to pick some. So the nice thing to do, well, I went through a couple, and I'm going to skip that to try and get to one that, because you not only, you have to pick, there are lots of ways to solve this equation, but then you want, when you you want them to be constant, each of the components to be constant rank. But the simplest thing to do is to say that this should be 1 and this should be -1. And a way to do that is to say that g of x1, x2 is x1 minus x2. So then we just need to have a function of p that is that when you write it like this, you get something that's linear. So f1, so we have 1 prime of p minus f2 prime of p needs to be, and actually let me just call these x's now. This needs to be linear and at some point equal to 0, but also you cannot have that both of these equal to 0 at the same time, right? Because then it would have non-constant. In order for it to be constant, f would have to be identically 0. Sorry, let me say that again. What we want is that this needs to be equal to 0 for some x, but we also required that big F was constant rank. So if both of these were 0 at some point x, then that point would have constant rank 0. So F would have constant rank 0, and we would be out of luck. So we need this. The easiest way to do this is to say, oh, let me do 1 plus x minus 2x. Now at 1, you get 0, but so this is equal to 0 if and only if x is equal to 1. So then I can write, I think I had this backwards. Sorry, this should be, sorry. Okay, right. So this is the interesting thing. If you try this, this unfortunately will give you some problems, I think. Sorry, where did this go wrong? G will not be constant rank here. Will it? Right, because it passes through 0. Okay, so I mean that's a good thing to show. This is one of the errors that I came across. So what I did is you say, okay, well,
G should be constant rank there because it's Jacobian. It's just a constant non-zero matrix.
Right.
So G is fine.
G is fine. Okay. Hold on. So let me just write down what I circled at the end. So at the end, what I said is that you have G of x1, x2 is equal to 1 plus x1, comma, and f of x is equal to x comma minus 2x. So why did I do that instead of this? Sorry, because this now, f would not be constant rank as written, right? Because if I anti-diff,
So F should be constant rank here still. Because to compute the rank of F, you just take a Jacobian, which is just the column matrix with F prime 1 of X in the first entry and F prime 2 of X in the second entry, right?
Right.
And that
but the
matrix
problem
is never
that
the
this-
zero matrix.
Is it never the zero matrix?
Yeah,
Because
that's
the Jacobian of this would be 1 plus X and 2X. These are not simultaneously zero.
exactly. Yeah, the second coordinate is only 0 if X is equal to 0, but then your
Right.
first coordinate is not 0.
Right, okay, so I'm not totally sure what I noted was an issue at some point.
Yeah.
Um,
Yeah, I think if you find F1 and F2, like the most obvious choices for F1 and F2, and then you can like take the Jacobian of those two entries. I think
yeah, I
those-
see what I
but
did.
Yeah,
This is what you would get. So yeah, so what I did, yeah, sorry. So I get to this by saying, well, I want this to look like, yeah, sorry. So again, apologies. What I did, and what I actually do is I say, okay, well, let's let this be equal to +1, and let's let this equal to -2, so that I can have something that goes through 0. And then I worked backwards to get that. Yeah, I mean, this works. Yeah. I don't remember my thought process for why I chose this one in particular, as opposed to what I wrote here. So sorry, that got messed up at some point.
yeah. So another option, and yeah, the trick here is what Raoul had right at the end of this box. Is that hey, when you take the product of
Which box?
the bottom of this box the natural box of the paper.
Okay.
Yeah. Is that when you multiply these two Jacobians, you get to add these two products together. So another way to do this is to let G be constant in like the first coordinate and be some variable, some function in the second coordinate, right? And let F be some function in the first coordinate and just constant in the second coordinate, right? Or X, so that way the derivative is constant, right? That way you know that your two Jacobians are never vanish because they always have one non-zero entry all the time. But then somehow when you take these products and multiply them together, that you get stuff that does vanish. Okay. So choosing something that so that way the Jacobian here, and I'm going to annotate on your page just to, right? So if you choose something here that's like 1x for this Jacobian, and something here that's like x1, right? Then neither of these, I don't know what happened to that second annotation. Then neither, okay, my second annotation is vanishing and I don't know why, which probably means that you're not seeing it, but I'm trying to write a column matrix for F1 prime and F2 prime, which is X1. I don't know why the zoom annotation is not working there. But that way, when you multiply these together and add them up, right, you get that the Jacobian is 2x, which is certainly not constant. And then you can just integrate as needed to find the function that you need.
Yeah, and in particular, yeah, so as you can see from the fact that I then got confused afterwards, this is the key point, that there are now infinitely many choices that you can make. The only thing that you need to require is that it passes through 0 while not being identically 0. So the easiest choice for that is a linear function or any odd function. And if you really hated yourself, you could do something of power 2, degree 2 or greater. But if anytime you have an even one, you have to actually make sure that it has real zeros. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . .
Are there any questions for Raul?
Yeah, again, I apologize for how this like suddenly took a nosedive.
Would you
But-
mind maybe typing up your solution to this problem and putting it on the doc so that way people can see a polished version?
Sure.
Because yeah, all the right ideas were here. These are the things that you should be thinking about to find the counterexample. But it'd be nice to just see the tail end of that polished up.
Yeah.
Cool. All right. So at this point, the only person left on the list is me for question 5. But I don't know if I can do me for question 5 in 10 minutes.
I can
do
talk about
as much of it
question
as you can?
4.
Oh, okay.
Or I mean, whatever. If people want to see question 5, I mean, I'd like to see it too. But if people want to see question 4, I can do question 4.
4 too, yeah.
Yeah, if you can if you think you can do question 4 in the 10-12 minutes, I think that would be great. And then I'll start off the day tomorrow by talking about question 5. And that one will probably take me a little bit of time to talk about.
Okay, is everybody cool with that? Okay, awesome.
Like 5 and 9, Jacob, because we didn't do 9, right?
I can do 9.
You can do 9. Okay, cool.
Right.
Yes, I
so,
haven't done 9 yet. I didn't have enough time after question 5 last night.
I bet.
yeah, so part A says let M be connected and suppose it has a show that if the fundamental group of M, if pi1 of M is odd, then there does not exist a 2-sheeted cover of M. So the fact here that we want to use is that if M is connected with finite fundamental group, actually, I'm not sure if we need the finiteness condition, but in any case, makes
I think you
sense here.
do. Also, sorry, I did lie. I can't count. I'm not doing number 9.
Okay.
Yeah, so the fact that we use is that if P is an unsheeted cover, then N is precisely the index of the subgroup of the fundamental group, which is the image under the induced map of the fundamental group of E. By Lagrange's theorem, the order of the fundamental group is equal to the order of subgroup times the index. Pi star pi. So N divides the order of pi1 of M if pi1M is odd, then N cannot be 2. And that's part A. Does anybody have questions on part A? Okay, and then part 2 says, give a counterexample if M is not assumed to be connected, or if M is not assumed to be connected, or if E is not assumed to be connected.
The covering, the upstairs.
Okay, yeah. If E is not assumed to be connected. So the trick here is to just figure out what is a space that has odd finite fundamental group. So the general construction that we can use to generate a finite, a space with finite cyclic fundamental group is to take S1 and attach a disk using the map from the boundary boundary D2 rather. That sends boundary element to 3 times it. So we take a circle and then we attach a disk along the boundary by wrapping it 3 times around S1.
Just for nicety, just write Z cubed, because that's what the actual complex map does.
Oh, right. You're right. Thank you. Yeah, Z cubed.
Z action 3.z that is defined to be Z cubed here.
Yeah. Yeah, you could also write it like that. So this should give this, I mean, I'm kind of being lazy here because I'm not sure the best way to actually prove this, but this space has fundamental group. Z mod 3Z. And then we can take just like 2 disjoint copies. We'll call the space M. Then E is sort of trivially a covering space where, just any point in M is evenly covered by the whole space, basically. So could probably say this nicer, but this is what I have for this problem.
You can cheat and make this even easier by letting your example just be a single point. Take your single point and have your fibers be just a disjoint copy of it.
So you're saying let M be a single point, or
Yeah. Let M be a single point.
Ooh, how does that have fundamental, like odd finite fundamental group then?
Its fundamental group is 1 point.
Yeah, it's the trivial fundamental group, which
I guess
has
that
one
is.
element.
I guess that does. Yeah, that does have odd fundamental group. Yeah, I guess I was overthinking that part. Yeah, good point there. So yeah, you could just take
Raul with
the
the just use 1 point arguments all seminar. Every
if you
time.
don't place
just
a
like, use 1 point.
restriction on Z or on your choice of N, you should always start with the smallest N you can find.
Yeah, so yeah, this is exactly how I think about it, because I just think of 2 disjoint copies. If you would like to write a more concrete map here, you can write M cross the points 1, 2, right? Just like the 2 set, right? 1 with 2 points, right? And then your map is just projection, right? And then you get exactly 2 sheets, 1 for each of those coordinates. So yeah, and that way you can like write out the map explicitly if you want, and then like prove that this is a covering map explicitly if you want. But also remember that you are writing this qual for Schultz. So I think that Schultz would be 100% okay by saying just take 2 disjoint copies and map them down via the natural identification. And he'd be like, yeah, give you a check mark, and you'd be, Okay.
Cool. Does anybody have any other questions? Okay, thank you.
Alright, cool. Well, thanks everyone for presenting today. This was really nice to hear you all talk about the math and hear how you all have been approaching some of these problems, which is great. There are two problems that people have not signed up for yet on this mock call, question 6 and question 9. And like I said, you all should feel free to add your own problems to that problem sign up sheet that I emailed
Oh,
out.
question 6? I can do question 6 right now if you want, like in literally 2 minutes.
I do have a quick announcement that I'm going to say
Okay.
real quick, but yeah. Yeah, so if people would like to sign up, I especially would like to encourage Catherine and Shanna and Vidir to sign up for problems, since you each only got to talk once today. And if nobody feels like signing up for problems, I guess I will have to sit down and do it, but hopefully you all are willing to do that or add other problems that other people can sign up for. I think that would be great. It looks like that we're going at the rate of 1 mock qual a week. So I guess that my job is to write a mock qual every week until the Topology Qual Prep Seminar is done, as a way to give you all lots of problems to do and think about. Just one thing before we go. So since you all presented today, I'm not going to have notes that I can upload like I normally upload to the page. So sorry if you're going to want to refer to what people did, you're going to have to watch the YouTube video that I post. But I did upload a Math Stack Exchange post about visualizing what the homology groups are supposed to mean. Right? I think that a lot of times we get into like compute this homology group and get that it's like Z4 or Z2 or Z or whatever. But I haven't talked about what the intuition behind it means. And when I was working on this question 5, I was just like, why should I believe that this first homology is Z4 plus 2Z, right? Or whatever it was that I got. And so, I did some Googling and I found this Math Stack Exchange post, which is great. It gives you like a nice like mental image for what these homology groups are supposed to mean and what spaces that have a certain number of like first homology generators are supposed to look like and stuff, which can be a really good gut check for when you're computing some homology and you get a thing and you're like, does this sound reasonable? Right? So feel free to go ahead and check that out. I think that's a really nice thing to have in your back pocket when you're doing some homology problems. Other than that, that's going to be it from me for today. So I'm going to stop the recording